So earlier we talked about why to study turbulence. That was the question we were trying to address. Why study turbulence? And we looked at different problems in nature. We talked about different examples in engineering, some important examples in engineering related to automobile aerodynamics, aircraft aerodynamics, combustion in an aircraft engine, some problems in nature, ocean turbulence, how it affects weather patterns, forest fires. Another example we looked at through a picture was the tip vortex behind an airplane wing, on an airplane wing. The wake behind the submarine, the hull of a submarine. So understanding turbulence is important in designing engineering devices, technological devices, and it is also important in trying to understand different things that occur in nature, weather patterns, wind patterns, climate change, the dynamics of the climate, things like that. So here I start with showing some examples that you would see in nature, some actual images that you would see in nature. I showed some examples of what we saw in engineering. The submarine was an example of that. And in this case, here I'm showing a satellite image of the Weddell Sea of Antarctica. So what does this show? It shows the image of a satellite image of flow around Antarctica. Right? So it's showing two ocean circulation features. The satellite image, as is written here, is about 240 by 320 kilometers. And the image reveals two large ocean circulation features. What am I talking about? These two, right? These are the two large circulation features, ocean circulation features, and we call them eddies. Now, this is at the northernmost edge of the ice pack in the Weddell Sea of Antarctica. These eddies play an important role in ocean circulation and the transport of heat toward the pole. The ocean eddies are 40 kilometers to 60 kilometers in diameter. So we are talking about this diameter approximately is 40 kilometers. Okay? So the dark areas are new ice and the light green areas are small ice floats are swept along by the ocean currents. First year seasonal ice is shown in the darker green areas in the lower right corner. The open ocean in the north, which is in the top, is blue. Okay, so this is the ocean. So this is an example of something that happens in nature. The eddies that we saw in the jet picture that I had shown earlier. This one, you are seeing similar structures. Okay, you're seeing similar structures here, except they are much bigger. They're much bigger in size, bigger in scale. Because the object that we are looking at, Antarctica, is much bigger in size. So this is an example of turbulence that we see in nature that has implications on, say, the ice formation in Antarctica, because it affects the way the heat is transported. So if the ice formation is affected, the weather changes accordingly. This has implications on weather patterns. This is an example of that. This is a prime example of that. Moving on, another example that you see in nature, the Alaska's Aleutian Islands. So here we are talking about the flow of air. As air flows around objects in its path, spiraling eddies known as the von Karman vortices may form. These are the von Karman vortices. The vortices in this image were created when prevailing winds sweeping east across the northern Pacific Ocean encountered the Alaskan Aleutian Islands. So the islands are an obstruction around which these vortices are created. Obviously, these will be much bigger in size compared to what? Compared to if I look at a cylinder and flow around it. This is a classic benchmark problem in fluid mechanics. Flow is going from left to right. I have a cylinder. I have obviously drawn it in 2D. The cylinder is into the screen. the length of the cylinder is into the screen, and I am drawing the flow around a cylinder. So what happens is, as the flow speed gets higher and higher, I will start to see patterns that are like this. I will start to see patterns that are like this. These are vortices that are forming behind the cylinder, behind compared to the direction in which the flow is coming from. Flow is coming from left to right, so on the right, that is behind the cylinder, I will have vortices being formed. These are von Karman vortices. These are, if you think about it, the cylinder in a typical lab experiment could be, say, 10 centimeter or even lesser, 5 centimeter. But you will see von Karman vortices that are of the order of that size, that are of the order of 10 centimeter. Here in the Alaskan islands, you will see von Karman vortices that are of the order of the size of the island. So the island acts as a bluff body. Just like the cylinder in the picture that I have drawn acts as a bluff body to the flow. Bluff body means as an obstruction to the flow. So that's an example of something that you see in nature. One last example. These are von Karman vortices, an image taken in 1999. Each of these swirling clouds is a result of a meteorological phenomenon known as the Karman vortex. Okay, something that you see in engineering, something that you see in labs. This is seen in nature. These are all satellite images. So the scale is pretty large. These vortices appeared over the Alexander Circuit Island in the southern Pacific Ocean, and rising precipitously from the surrounding waters, the island's highest point is nearly a mile, 1.6 kilometers above sea level. As the wind-driven clouds encounter this obstacle, they flow around it and form these large spinning eddies. So again, the island acts as a bluff body. It is acting as an obstacle to the flow. It is obstructing the flow. And the flow around it creates this von Karman vortices. Look at this. Isn't this similar to what you see for flow around a cylinder? You would see these exact patterns at a much smaller scale in flow around a cylinder. So what we are talking about is the similarity. Okay? The similarity that you see for a lab experiment, for turbulent flow in a lab experiment and turbulent flow in a much larger scale where you have flow around an island. These are trying to understand the flow in this picture here. Okay, has a lot of implications in trying to understand the weather dynamics in that area. How the weather changes, how hot do some of the seasons get, how hot does summer get, how cold does winter get, because these flows affect the transport of heat, which means it is important to try and understand turbulence. So in a sense, this is all a continuation of the question we were trying to answer earlier. Why study turbulence? This is an example of something that we see in nature where it is important to understand these patterns. It is important to understand what implications these patterns have. Are these patterns going to recur every year, every month? If they happen more than usual, does that change the weather in that region? It's these kind of questions that we need to answer in order to understand why we need to study turbulence. So the first question was, why study turbulence? And I believe we have tried to cover some of the main aspects of why we need to study turbulence. We talked about a lot of different examples, both in nature and in engineering. Now the next question we would like to answer is, what is turbulence? Right? Before learning a topic, we need to understand, okay, why? Why are we studying this? There's a motivation to study this, and I believe we have covered that. So now that we have understood why we need to study it, okay, what is turbulence? Right? I talked about the difference between laminar and turbulent flow. I talked about how they are different in terms of flow characteristics, some basic characteristics. Is that how we define turbulence? So here, this slide sort of tries to answer the question of what is turbulence in a more philosophical manner. So I start with an illustration of a very famous fable where you have the 6 blind men and an elephant. Each blind man touches a different part of an elephant and makes his own assumptions about what that part is. One person is sitting on top of the elephant. Remember, he is blind. He doesn't know what is in front of him. He doesn't know what he is touching. He feels one part of the elephant. Say he is feeling the top of the elephant. He looks like he's feeling the ear of an elephant. And he makes an assumption that it's a fan. Another fellow here is on a ladder. He's touching the body of an elephant and he feels that it is a wall. Another fellow here is holding on to one of the legs of an elephant and he feels that it's a tree. This fellow here touches the tusk of an elephant, feels it's a spear. This guy here touches the trunk of an elephant and feels it's a snake. And the very last fellow is at the back. He is touching the tail of an elephant and he feels it's a rope. So there are a couple of things that I want to show here. Okay? Now, philosophically, these 6 people are looking at different parts of the elephant and making their own assumptions. They actually don't know what it is, and they are making their own assumptions about the animal. Turbulence could be like that. In fact, you will see that there are multiple interpretations of how one defines turbulence. I'll go over that. From the 19th century to now, scientists, people have been coming up with different definitions of turbulence. What they see in turbulence, how they would describe turbulence. Obviously, we have converged to a more modern definition of turbulence and we will cover that in this class. But this is how the understanding of turbulence and the need to answer the question of what is turbulence has evolved. It's a fan, it's a spear, it's a snake, it's a tree, it's a wall, it is a rope. Okay, different interpretations. That's one aspect. Now, interestingly, this picture also has other implications for the specific topic of turbulence. How is that? The different structures that you see in turbulence, okay, you could have flat structures, you could have long structures, short structures. I talked about earlier how the scales are different. When you look at some of the structures in turbulence, you could have all these different kinds of structures. Structures that look like ropes, structures that look like fans, structures that look like trees. So in a way, interestingly, some of these interpretations that the blind men have, okay, are very similar to the structures that you view in turbulence. And that is the second aspect of this picture. The first aspect is, of course, the philosophical aspect of how it is so difficult to understand turbulence that scientists make their own interpretations of it. What they observe. I'm not saying they are making a wrong interpretation. I am saying that they try to define turbulence based on the observations, based on what they see. The second aspect is related to the actual structures of an elephant and how they are similar to what you actually see in turbulence. It could be like a fan, it could be like a rope, okay? A long rope, a short rope, a tree-like structure, very large structure, very small structure like the rope, a very flat structure like the fan, or like the ear of an elephant. That is the second aspect of this picture. So moving on, if I look at some of the descriptions of turbulence, because I have to answer the question, what is turbulence, right? These are some of the descriptions of turbulence. Believe it or not, turbulence was already recognized as a fluid behavior, as a distinct fluid behavior 500 years ago. By whom? By none other than the genius Leonardo da Vinci. And this is what was found in one of his books as a sketch. I'll come back to the description in a bit, but look at the sketch he made of turbulence. What does this look like? This is what he described as a turbulent flow. He called it turbulenza. He termed it turbulenza, okay, which is where the word turbulence comes from. The modern word is obviously turbulence. And what has he described, or what has he actually drawn here? It looks like water is gushing out from some kind of nozzle, we can call it a nozzle, but from some kind of a tap. It's flowing into a container, and the water is flowing so vigorously that it is getting mixed in that container so much. And you see these patterns that are formed, patterns that are irregular, patterns that are disorganized, patterns that are chaotic. These are some of the observations we've been making, right? So he drew this and he described it in the following way. Observe the motion of the surface of water, which resembles that of hair. So that's the first observation he makes. It resembles that of hair, chaotic, disorganized, which has two motions, of which one is caused by the weight of the hair and the other by the direction of the curls. So this part is interesting. Let me finish the definition before I describe what significance this part has. The two motions. Thus the water has eddying motions, one part of which is due to the principal current and the other due to random and reverse motion. The smallest eddies are almost numberless, and the large things are rotated only by large eddies and not by the small ones. And small things are turned by small eddies and large. Now, one can actually see this as a definition of turbulence. Obviously, Da Vinci was just putting down his observations of what he saw in the flow of water. But there's a lot of meaning in the sentences here. Two motions, one caused by the weight of the hair. So when he describes the hair, he talks about two motions. Then he moves on to describing the motion of water. Water has eddying motion. So one part of which is due to the principal current and the other part is due to the random and reverse motion. The smallest eddies are numberless and the large things are only rotated by the large eddies and not by the small ones. Simply put, he is describing the energy cascade of turbulence. He is talking about large scales versus small scales. We saw that in the jet picture earlier. You have a jet, you have the large structures, and then you have the small structures. He talks about how the small structures, the small eddies, are numberless, so many small structures. Large things are only rotated by the large eddies and not by small ones. What he is trying to say is exactly the energy cascade. The energy goes from the large scales to the small scales. Now we'll describe more of this in a much more systematic and sophisticated way as we learn more details about turbulence. But for now, understand that energy flows from the large scales to the small scales and not the other way around. Unless there's an exception, there are some exceptions, and we'll discuss that later. But just think of his observation. He is talking about two kinds of motions, even when he talks about hair and even when he talks about water. two kinds of motions, always two parts. And that is what we describe as large structures and small structures. And the energy cascade is also something that he's covering. So this is the picture that he drew 500 years ago. Now just imagine the implication of that. This is somebody who came up with the first description of turbulence. I wouldn't call that a definition, but a description of turbulence which is close enough to the definition that we have today in the modern world. Now, I'll take a leap to a few decades, to a couple of centuries later, and then talk about the Navier-Stokes equations. So this is one set of equations that pretty much embodies the physics of all fluid flows, whether it is laminar or whether it is turbulent. So for turbulent flows are described by the Navier-Stokes equations. Okay? And these were introduced in the 19th century by Navier and Stokes. There's one additional point that I want to make here. This is within the confines of the continuum hypothesis. When you talk about fluid mechanics, definitely in turbulence, we talk about the continuum hypothesis being invoked. Okay? And the Navier-Stokes equations within the confines of the continuum hypothesis describes the turbulent flows. What do I mean by continuum hypothesis? What we are trying to say is the fluid is described as a continuous media and not as a set of discrete molecules. So we are looking at the fluid macroscopically, not microscopically. We do not care about what happens between one molecule to the other. Obviously, the fluid is made up of millions of molecules, billions of molecules. We know that. But for us, every property of the fluid is an average of a volume that contains millions of molecules. So if I take the density of a fluid, right? The density of a fluid at a particular point is an average of all the molecular properties of all the molecules in that box, in that volume. Now this itself will be pretty small, but we are not looking at it at every molecule per se. We are looking at just a volume. So that is what the continuum hypothesis is. That means it is determined by something called the Knudsen number, which is defined as lambda over L. Again, we are bringing in the L, and L is again the characteristic length scale. Lambda is the mean free path The mean free path is the average distance one molecule has to travel before it collides with another molecule. So obviously that is going to be a pretty small number, right? Because the distance between two molecules sort of determines the mean free path. L is the characteristic length scale. For the continuum hypothesis to be valid, Knudsen number has to be very small, much less than 1. That's what the continuum hypothesis is. So in most applications, especially engineering, and in most of the applications in nature, the Knudsen number is very less than 1, is a very, very small number. So that means the continuum hypothesis is valid. That means the Navier-Stokes equations can be used. Coming to the Navier-Stokes equations, what is described here, equation 1 and 2, is a simple form appropriate for the analysis of incompressible flows. What do I mean by incompressible flow? The density is a constant with respect to pressure. That's what I mean by incompressible flow. I have two equations here that are described. The first one, equation number 1, is continuity, which is del dot u is equal to 0. Originally, there is a term which is represented by del T rho plus. That means it is the rate of change of density with respect to time. But because the flow is incompressible, this term goes to 0 because of the incompressible assumption. Then I have a del dot u is equal to 0. Remember, u is a vector, and I have the divergence of velocity being equal to 0. That is the continuity equation. The second equation is the momentum equation. I have ut, the first term. This is the transient term, time rate of change of velocity. The second term is the convection term. The third term is the pressure gradient, PR grad. The fourth term, as in the second term on the right hand side, is the viscous term. And the last term is the body force term. This could be gravity, this could be buoyant force or gravity, this could be some kind of centripetal force, some kind of magnetic force, depending on what the application is. But these are your Navier-Stokes equations. This is what describes turbulent flows in general with the continuum hypothesis. So what have we done? We started with the first description of turbulence by Da Vinci. How that had implications on the modern definition of turbulence. We talked about how his description of turbulence involved the description of large scales and small scales in his own words. How it involved the description of energy cascade in his own words. And then we jumped to how the Navier-Stokes equations are still used as the description of turbulence. It does not describe it in words, but mathematically this is what describes all fluid flows, so it describes turbulent flows as well, within the confines of the continuum hypothesis. Thank you.